Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been looking at various modules earlier, and now presently we are looking at this module on space vector based PWM. So, initially we looked at the concept of space vector, and where we it is like the rotating MMF in a machine, and we went on to define look at 3 phase currents and how they can be transformed into equivalent 2 phase currents or current space vector, and we looked at the transformation of 3 phase voltages into a space vector and so on. So, we just looked at the concept of space vector and space vector transformation, and the last lecture we also looked at this conventional space vector PWM, which we would kind of review in this particular lecture. And this lecture would emphasize on space vector based bus clamping pulse width modulation. This bus clamping pulse width modulation or this discontinuous pulse width modulation is something we discussed in the earlier module on triangle comparison based PWM. So, there were a few couple of lectures where we discussed with these kind of discontinuous bus clamping PWM. Today, instead of space vector, instead of triangle comparison, we are going to do the same thing using space vector, and we are also going to see how the two approaches are equivalent. That is a triangle comparison, which we discussed in the previous module, and space vector, how they are equivalent. So, even in the last lecture, we just slightly saw that in the context of conventional space vector PWM. Today, in the context of both conventional space vector PWM and the so called bus clamping PWM, we will see the equivalence between these two approaches, that is the triangle comparison approach and the space vector approach, right. So, the next lecture we would hopefully look at space vector based advanced bus clamping PWM. As I was saying, the equivalence is well known and is widely understood and discussed in the literature, but what I would like to say is space vector approach is kind of more general than the triangle comparison approach. With space vector approach, you can produce certain PWM waveforms which cannot be produced by triangle comparison approach, and some PWM methods is called this advanced bus clamping PWM are exclusive to space vector based approach. So, which we would hopefully discuss in the next lecture now. So, let us quickly take a look at space vector transformation. We are going to discuss on space vector based bus clamping PWM. Let us just start off with space vector transformation. Let us say there are 3 phase currents IR, IY and IB, and which sum up to 0, that is IR plus IY plus IB equals 0. In such a situation, we have seen that IR, IY, IB, the 3 phase currents can be transformed into two phase quantity, because IR plus IY plus IB equals 0 is what you said, it shows that IR, IY and IB are not independent, right. And so, they can be, and IR plus IY plus IB is equal 0 is similar to the equation of a plane x plus y plus z is equal to 0, and a plane has only 2 dimensions, and it can be spanned by 2 orthogonal vectors. So, IR, IY, IB, though 3 phase quantity, can be represented by 2 independent quantities I alpha and I beta, that is the idea, and I alpha is simply equal to 3 by 2 times IR, and I beta is equal to root 3 by 2 times IY minus IB, and these orthogonal quantities we are taking them such that alpha axis is aligned with R phase axis and beta axis is 90 degrees ahead of alpha axis. And so, this is I alpha I beta written in terms of IR, IY, IB as a in the matrix form. So, this matrix is the transformation matrix for space vector transformation, right. So, let us just similarly you have 3 phase voltages VRN, VYN and VBN, which sum up to 0. Now, these 3 phase voltages can also be transformed into 2 phase voltages V alpha and V beta shown here. So, V alpha is equal to 3 by 2 times VRN, and V beta is root 3 by 2 times the difference between VYN and VBN, or VYN minus VBN. So, the same thing is written in the matrix form here. So, when we look at a 3 phase inverter, the output voltages are fixed levels, it has only 2 levels, it is a 2 level inverter. So, it has only 2 levels here, either plus VDC by 2 if it is connected to the top throw, or minus VDC by 2 if it is connected to the bottom throw. There are only 2 levels here now, and so every voltage can have 2 different levels. There are totally 8 sets of output voltages are possible, and these here again I have just shown that as top device and the bottom device here. So, your R, Y and B can be either plus VDC by 2 or minus VDC by 2 with respect to this midpoint O. So, 8 sets of output voltages are possible, as I said before, and you are applying this output, the outputs are connected across a load, the load is taken like this RYB, a 3 phase balanced load, and it has a common point, it has a neutral point n. This neutral point n is not physically connected to the inverter. Sometimes it can be connected to the DC midpoint O, or through some appropriate filters, and many things are possible, or some other components can be connected here, and there is some filtering and all that. Now, we are assuming that we are having a 3 phase star connected load like this, where the neutral is not connected anywhere, right. They only R, Y, B and B are connected to the inverter now, that is the kind of load now. So, your VRO can take the values of plus or minus 0.5 VDC, as I have been mentioning probably from my very one of the early lectures. And so, corresponding now V alpha and V beta we have defined the space vector. In the last 2-3 lectures we have been discussing this. So, that V alpha is equal to 3 by 2 times VRN. I have pointed out to you that this is VRN, this is the phase to neutral voltage applied on the load. This is not VRO, this is not the R phase voltage measured with respect to the DC midpoint, but this is the R phase voltage measured with respect to the load neutral N. Same way V beta is root 3 by 2 times VON minus VBN, this is space vector transformation now. So, VRN can be replaced in terms of VRY and VBR, the line to line voltage is shown here. They in turn can be replaced in terms of the pole voltages as shown here. So, this is V alpha in terms of pole voltages, this is V beta in terms of pole voltages, and you can see that V beta is independent of VRO. So, this is something that you have here. And we also looked at for 8 sets of values of VRO, VYO and VBO, for 2 sets of them VRO, VYO and VBO are equal, that is 0 state, all 3 are equal to plus VDC by 2 or all 3 are equal to minus VDC by 2. It is easy to see that when VYO and VBO are equal, V beta is 0, and when all the 3 VRO, VYO, VBO are 0, this is also equal to 0. So, the 2 0 states lead to V alpha equal to 0 and V beta is equal to 0, that is they lead to a null vector, and all the other states lead to vectors of magnitude VDC. These are called active states and the corresponding vectors are called active vectors. We saw this in some detail in the previous classes and we quickly reproduce here. When R phase alone is connected to the positive bus and Y and B are connected to the negative bus, the inverter produces a vector which is aligned with the R phase axis as shown here. And when the state is inverted, when R is negative and Y and B are positive, you go around like this, you get the negative vector now. Like plus minus minus, R alone is positive here, if Y alone is positive and the other 2 are negative, you get a vector which is aligned along the Y phase axis. Similarly, B alone is positive and the other 2 are negative, you get a vector of the same magnitude VDC along the B phase axis now. So, thus you get these 6 vectors as we saw in the previous lectures now. So, in space vector based PWM, what we would do is we have this revolving voltage vector which we just saw here. So, this is the revolving voltage vector which has been indicated here. So, instead of using 3 phase modulating signals, we use a revolving voltage vector which is having a constant magnitude and angular frequency at steady state. This magnitude is gives a measure of the amplitude of the AC voltage that you want, and this angular frequency is it is the modulation frequency that you want. It is a fundamental modulation frequency, right, omega, which is equal to 2 pi f, where f is the modulation frequency. In space vector based PWM, you use such a revolving voltage vector instead of 3 phase modulating signals, and this voltage reference vector is sampled every subcycle, and the sampled value of the reference vector gives the voltage command for the inverter. And so, if you consider a revolving voltage vector and it is sampled at equal intervals of time, you are going to get samples like this, as I had said before. And in any particular subcycle, you may have a commanded reference vector, say like this or say like this. When you have a commanded reference vector, so say this is the vector, what you do is you try to produce this by time averaging these vectors V1, V2 and null vector. So, if you apply V1 vector for some t1 seconds out of ts seconds and V2 vector for t2 seconds out of ts seconds, so and null vector for the remaining time, what you get is you get this effective average vectors you want now. Thus, you can see that the time t1 and t2 should be related to this Vref and alpha. So, you can work that out. So, this is the volt second balance, V reference into Ts, that is what is the required voltage, and what is applied is V1 for T1 seconds, V2 for T2 seconds and Vz for Tz seconds. These two have to be equal. So, that is the volt seconds are equal over a subcycle duration time. So, Ts is T1 plus T2 plus Tz. So, this being a vectorial equation, there are 2 equations here, there is one equation, 3 equations. 3 equations, 3 unknowns, you can solve for them. You can get T1, T2 and Tz, T1 and T2 in terms of Vref and alpha like this, and Tz is Ts minus T1 minus T2 as we saw in the previous lectures now. So, this is how you calculate the dwell times for all of them. This is in space vector based PWM. Now, if you are using conventional space vector PWM, what you would do is you want to apply active vector 1, active vector 2. You would start from the null vector, go to active vector 1, active vector 2 and come back to the null vector. However, this null vector is produced by 2 different null states, 0 states. One is minus minus minus, which we designate as 0, and plus plus plus, that is all the top devices being on, which we designate as 7. So, what you do is, in fact, it is not just in conventional space vector PWM, this is true about all continuous PWM, wherever the modulation signals are continuous. I will emphasize this a little later also. So, it is also true in sine triangle PWM as we saw last time. You start from say minus minus minus, and then you switch one phase. In this case, it is the R phase which gets switched first, and you go to the vector, one active vector. You switch the second phase, you go to the next active vector. You switch the third phase, you come back to the null vector, but it is not the same 0 state, it is the other 0 state. In the next subcycle, you start from this null state and switch in the reverse sequence, B phase first, Y phase next and R phase third, and you reach here now. So, this is the kind of switching sequence you use now. So, you apply this for T1 seconds, you apply for this for T2 seconds. Before going here, you apply this minus 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 for Tz by 2 seconds. You stay here for Tz by 2 seconds and go here and stay for T1 seconds, go here and stay for T2 seconds, and then come back here and stay on this plus 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 for Tz by 2 seconds and do the reverse process. So, this is what is indicated in this diagram. So, you are given a reference vector, you are sampling it, and once you have that sample, you have the value of Vref and alpha. Using the values of Vref and alpha, you are calculating T1, T2 and Tz, and you are dividing this Tz equally between 0 and 7, T0 is equal to T7 is equal to 0.5 Tz, and you are outputting the inverter states like this. That is what you do in space vector based PWM. So, the R phase voltage now it varies like shown here. You see that it has the highest duty ratio of the 3 phases here, and Y phase has a duty ratio which is kind of close to 0.5, or an average voltage is close to 0, and VBO has the lowest duty ratio, as you can see from here. So, this happens because in this particular case the voltage reference vector is close to the R phase axis, and it is close to the B phase negative axis, R phase positive axis and B phase negative axis, and it is also close to the Y phase 0 crossing. If you talk in terms of the 3 phase sine waves, this the 3 phase sine waves are such that the R phase value is close to the positive peak, the B phase value is close to its negative peak, and Y phase value is closer to its 0 crossing. That is what you have, and you get these kind of patterns here, right. So, we emphasized on the equivalence now. So, once you have those things, you can consider the average values VRO average, and which is shown here in the red dashed lines, and then you have this green line which stands for the yellow phase here, and you take the average value, it is some average value very close to 0, and similarly VBO has some average value like this now. You can take a scaled version of this average VRO average, you can call it MR star, and a scaled version of VYO average you can call it MY star, and scaled version of VBO average you can call it MB star. If you have MR star, MY star and MB star, what you can do is you can compare them with the triangular carrier as shown here now. If you compare these equivalent modulating signals with a triangular carrier, you can get the same switching instance. So, these switching instance can not only be arrived at by starting from the voltage reference vector, the sample of the voltage reference vector, and calculating the values of dwell times and outputting the inverter states. You can also go the other way. You can also start from these equivalent modulating signals and compare the equivalent modulating signals with triangular carrier. So, what are these equivalent modulating signals is a question which you can find out. So, if you see this VRO average as I told you is a scaled version of MR star, and VYO average is related to MY star, and so on now. So, the equation for VRO average is given to you now. So, for the time during the interval T1 plus T2 plus T7, VRO average top device is on. For during the interval T0, VRO's bottom device is on. Therefore, the pole voltage here is minus VDC by 2, and this is the expression for the average voltage of VRO. Similarly, for VYO average, the top device is on during T2 plus T7, and the bottom device is on for T0 plus T1. Therefore, this is the average voltage now. Again, for VBO average, the top device is on only during the interval T7, this is on during the intervals T0 plus T1 plus T2. So, like this you can do the calculation now. So, you can just complete this. So, you will have different expressions for VRO average, VO average and VBO average in the different sectors as I mentioned before, and you can consider this as you can go about deriving an expression for this 3 phase average pole voltages are the equivalent modulating signals as I mentioned earlier. Now, I would still leave that as an exercise to you now. So, you will find if you do that average voltages etcetera, you will find that these 3 phase average voltages are these are not sinusoidal waves, these are sinusoidal waves. MR star for example is not a sine wave, but sine wave with some common mode component added to that. Now, you can also start from rather than this space vector PWM, conventional space vector PWM, we can also start with sine triangle PWM. Consider one carrier cycle, consider these signals, these are the modulating signals for R phase, Y phase and B phase, right. So, these are the sampled values of sine waves, the 3 sine waves during over one carrier cycle. Now, you look at the switching instance now. So, these are the wherever they intersect, the carrier and the modulating signals intersect the switching instance now. During the start of this carrier cycle, which is the falling carrier cycle, all the phases are low. Therefore, R in R phase bottom device on, Y phase, B phase are also the bottom devices are on. So, all the 3 phases the bottom devices are on, therefore, you have this so called 0 state 0 minus minus minus. Then R phase alone switches, then you have the state 1 plus minus minus, then Y alone switches, then you go to the state plus plus minus, then B switches, then you go to the state plus plus plus. Then the same thing happens in the reverse direction, and you see this is the exact sequence that you use, like even a little before we did this now. So, this is exactly you start from 0, 1, 2 and 7 and you are coming back like this. So, this is in conventional space vector PWM. We see that in sine triangle PWM also it is pretty much the same thing. The only difference is in space vector PWM both are applied for equal durations, T0 is equal to T7 is equal to 0.5 Tz, whereas in sine triangle PWM T0 is not equal, typically not equal to T7. So, that is the difference now which has been pointed out here, that is sorry. Yeah, you can see that this is not equal to this. So, these can be made equal to one another. Now, we do not want to change T1 and T2, right, we do not want to change T1 and T2, but we want to slightly adjust T0 and T7 such that their sum does not change now. What can we do? We can add a small common mode component. Let us say I add a common mode component to VR and Vy and Vb, a small delta V is added, positive delta V is added to all the 3. What will happen? VR will slightly go up, Vy will also go up to the same extent, Vb will also go up to the same extent. Once all the 3 signals go up to the same extent, what will happen here? The 3 switching instance will move to the left to the same extent. Now, T0 will reduce, this switching instant will also move, but T1 will not change, and again this switching instant will also move, but T2 will not change. So, what will have effectively happen is T0 will reduce and T7 will increase, but the sum of T0 plus T7 will remain the same. T1 is unchanged, T2 is unchanged. So, when you add a common mode component, the active vector times do not change. I will be making this statement again and again, please bear with me, but that is very important for us to realize. When you add these common mode components, what happens is T0 and T7 change, but their sum again would not change. So, now what you can do is, if you can see here, T7 is a little bigger than, is a little longer than T0. So, what you should do here is to add a small negative common mode voltage to all the 3. You must add a negative common mode voltage such that T7 reduces and T0 increases and both of them become equal. So, this is what you can see from this illustrative example, and we can do this quantitatively. We did this even in the last class, which we will do this again now. So, as long as T0 and T7 may change, but T0 plus T7 their sum is unchanged. So, the null vector time Tz is not changed, the active vectors times T1 and T2 are not changed. So, you will get the same reference vector, right. So, this is how the switching sequence goes, as I just mentioned there, but only thing is T0 is not equal to T7 as I mentioned here. If you want to make the null vector time equal, this is what we are coming to. So, what we simply do is, let us say this MR, My and Mb, MR, My and Mb, MR turns out to be the maximum value, My turns to be the middle value and Mb turns out to be the minimum value. This is in sector 1. In different sectors, different things will be middle. If you go to sector 2, for example, R phase will be the middle value. If you go to sector 3, Y phase will be the middle, B phase would be the middle value and so on and so forth. So, now in any phase you will have 3 signals, one of them will have the maximum value, will be most positive, another one will have the minimum value or the most negative value, and the third one will be the closest to 0 and that is M mid. So, let us call this M max, M mid and M min. Now, you want to add common mode. So, that common mode is MCM. So, you define M max star, M mid star and M min star, which are obtained by adding MCM to M max, M mid and M min respectively. So, as I have defined here now. So, what do we want? We want the null vector time to be equally divided between the two 0 states. If that has to be equally divided, then M max star should be equal to the negative value of M min star, that is what is needed. So, that your T0 and T7 times will be equal now. So, if M max star plus M min star should be equal to 0 will be the condition for the null vector time being equally divided. So, what is M max star? It is M max plus MCM. What is M min star? It is M min plus MCM. Therefore, you get this equation M max plus M min plus 2 MCM is equal to 0. So, from this you get the expression MCM is minus 0.5 times M max plus M min. And what is M max plus M min? It is minus M mid, because these are sinusoidal signals. So, M max plus M mid plus M min is 0. Therefore, you get 0.5 M mid. Remember, M max plus M mid plus M min is equal to 0, but M max star plus M mid star plus M min star is not equal to 0. That is equal to 3 times the common mode signal. So, if you want the division of null vector time to be equal between the two 0 states, what you need to do is you have to add a common mode component which is simply 0.5 times M mid. And this is what I have said before, that if you want to implement space vector PWM, conventional space vector PWM, rather than starting from the other end, that is you start with revolving voltage vector and sample, and then use the sample and calculate the times. If you have to calculate the times, it is sin 60 minus alpha and sin alpha are all needed. So, you typically need sine tables. So, the values of the sine values of different angles from 0 degree to 60 degree need to be stored in a lookup table, etc. From that you have to do those calculations, and then you have to output the waveform. Rather than doing all that, you can easily implement using triangle comparison approach. How? Just as in sine triangle PWM, you start with 3 phase sinusoidal waves, and you always find out the middle value and take 50% of the middle value and add it, and that will give you the signal, and you compare that modified MR star, MY star, MB star with your triangular carrier, and that is your sine triangle PWM. And this it provides 15% higher voltage, as I will also show you a little in a while. And this actually combines the advantages of 1/6 third harmonic. This 15% additional voltage, if you recollect the third harmonic injection, if you add 1/6 third harmonic injection, we can get 15% additional voltage. So, that is what I am saying here, you are going to get that 15% again here. And what happens is, like in the 20, like in 1/4 third harmonic, the THD is also low. Actually, the THD is closely related to how the null vector time is divided between the two 0 states. We are dividing the null vector time equally here by doing this. So, when the null vector time is and in the third harmonic case with 1/4 third harmonic injection also, the null vector time gets more or less divided equally. So, the THD that you get is the line current distortion is pretty low in these two cases. So, conventional space vector PWM can be said to have the advantages of these two together. Of course, about the line current ripple, etc., we will look at it in the next module, when we will particularly be dealing with the evaluation of line current ripple now. So, what I was just trying to do is, this previous one that you have this common mode is equal to 0.5 M mid, let us just try and get a feel for this one. So, what I will do is, let me choose my horizontal axis and vertical axis now. So, I am starting from R phase, at 0 crossing is where R phase has got its 0 crossing. I am plus trying to plot M mid. So, 0 degree to 30 degree, if I look at 0 degree to 30 degree, which phase has the lowest one? It is the R phase has the lowest one. So, let us say this goes like this now, this is 0 to 30 degree now. So, which is the other phase that is going to cross now? The B phase would have a negative 0 crossing now. Let me just change it to color. So, the R phase would go like this, the next middle value will be somewhere like this, and this will see your 90 degrees. Then it would be the yellow phase. Let me choose a green color for that. So, the yellow phase would be the middle valued phase here. This is like 150 degrees. Then 180 and goes till 210 now. So, what I am trying to say here is you have 3 phase modulating signals. Now, in the first 0 to starting from 0 degree, 0 to 30 degree of the 3 phases, it is the red phase that has the middle value. So, B and Y are one higher and the other one is lower, M max and M mid. Then at 30 degrees what happens, the B phase R phase increases beyond some value and B phase reduces beyond this, and this value is 0.5 times Vm, the maximum peak of this now. It is sin 30, whatever is your Vm sin 30 is this value now. So, then the B phase has the middle value sine. So, of the 3 sines, it is the B phase sine that has the middle value here and it comes something up to this point. Let me also write this value, sorry. So, this is going to be 0.5 times Vm, because it is Vm sin 30 degree. And in the initial portion between minus 30 and plus 30 degree, the sine wave is going to look almost like a straight line. That is why I have drawn it almost like a straight line. Then it is B phase, it is B phase, then it is the yellow phase. So, 120 degree is the 0 crossing of the yellow phase waveform, 90 degree and 150 degree between this yellow phase as the middle valued modulating signal. The absolute value of the yellow phase is low in this region, after that it is R phase again now. So, this is M mid, and what is 0.5 M mid? Let us just draw that. So, just 0.5 M mid is like this. I am drawing throughout in the same color. So, this is 0.5 M mid in over half carrier cycle, I mean a half line cycle. It goes on in the other places also, right. So, you see this is the common mode component added. This common mode component looks roughly like a triangular wave. It looks roughly like a triangular wave. It has a peak value of something like 0.25 Vm. It is not exactly a triangular wave, it is a sinusoidal signal, but since sine closer to 0 crossing, sine looks like a straight line. So, it is something like this now. This is added as a common mode to the 3 phase sine waveforms, which I am going to show now. This is the original sine waveform, like say that this is the R phase sine waveform, what is shown in the dotted line, and this is the waveform that I hand drew earlier, and this has been plotted using a computer program. Okay. When I add up these two, the R phase waveform and this common mode component, what happens is you see that since the common mode component is positive here, this is more than that, MR star is greater than MR, and at this instant, which is actually 60 degrees, common mode component is 0. At that instant, MR star is equal to MR. Between 0 to 60 degree, MR star is greater than MR, because the common mode component is positive. And at 30 degrees, you can see the change in slope, because the common mode component slope changes there. It's discontinuous, the slope is discontinuous there. This function MCM is indifferentiable at that particular point, right. So, you can see that here also, and what happens is then it becomes the same value, and here it is negative peak. So, when MR is having its positive peak and it is equal to Vm, MCM is having its negative peak, and this is how much? Vm, and how much is this? This is 0.25 Vm, this is minus 0.25 Vm now. So, Vm sin 30 is 0.5 Vm, so this is half of that, so in minus 0.25 Vm. So, what you have here is something like 0.75 Vm is what you have there. And now, so this is your MR star, and once again you see that there is something here. So, it has a turning point here, again it has a turning point here, and there is a change in slope and it comes back here. This is MR star. The same way you have MY star and MB star, which are all phase shifted, time shifted by 90 degrees, by 120 degrees, right. So, now you can make a few clear observations. You see this is your MR and it has some peak, and I have taken it as 0.8, though it is not very clearly readable here, it is 0.8 now. And MR star, if you see, has a lower peak value, because whenever MR is going close to its peak, the corresponding common mode voltage is negative, and therefore, it brings down the value of MR star. So, this value is lower. So, what can you do? It gives you the possibility of making this original sine waveform's peak greater than that of the triangular peak, just as we did in third harmonic injection. So, now we are analyzing conventional space vector PWM. We have shown that it is equivalent and we are trying to do the analysis from the triangle comparison approach and understand this better now. Here I am showing it for 1.15, which is roughly 2 by root 3. So, if I take it like this, you see that now the sine wave goes above this horizontal line is 1, this is 1 actually, if you can see that this is 1, and therefore, now this line is 1. You can see that it goes above that, it goes something like 1.15. But what is happening? You are adding a common mode component like this. Because of adding this common mode component, this peak is coming down here, and the peak of MR star is just touching 1, and 1 corresponds to the peak value of the positive peak of the carrier, minus 1 corresponds to the negative peak of the carrier. Though the sine wave has a peak value of 1.15, the or 2 by root 3 actually speaking, the MR star, MY star and MB star, they only have values equal to 1, which is the peak of the carrier. Thus, without going into over modulation, you are able to increase your AC output. So, your AC output increases by 15%. This is a claim that I made a couple of slides back, and even I made this claim in the last lecture also. I am just demonstrating that, I am proving that in one particular way. This can also be proved in the space vector terms itself. You can see what is the highest value of Vref, which we will do it, and from there you can come to this. In fact, for all the space vector based PWM methods, the voltage can be 15%, the AC voltage can be 15% higher than what you can get with sine triangle PWM, not only for conventional space vector PWM, we will discuss this a little later, right. So, this is what now you can see that this is from the looking at the 3 modulating signals or the 3 equivalent modulating signals, you can very clearly understand that conventional space vector PWM gives you 15% higher fundamental voltage than what sine triangle PWM can give for the same DC voltage, right. So, we just go into the variant, which is what I actually want to discuss in this class. One of the main things is about bus clamping PWM, the other thing is on the equivalence. I dealt with the conventional space vector PWM at some length today, just to underline the equivalence between the triangle comparison and the space vector approach. So, now let us look at what we call as the clamping sequence. As you see, you want to apply null vector, you want to apply active vector for t1 seconds and active vector 2 for t2 seconds, you want to apply null vector for tz seconds. It does not matter whether you apply 0 or 7, you can produce the same average vector. This average vector can be produced if you apply this for t1 seconds and this for t2 seconds and the null vector for tz seconds. It is not necessary that you can apply both of them for equal, this 0.5 tz and 0.5 tz, or this can be 0.4 tz, this can be 0.6 tz, this can be 0.2 tz, that can be 0.8 tz, or as a special case only this state can be applied for the entire tz, or only this state can be applied for the entire tz. Now, we are considering a particular situation where we are totally ignoring the 0 state plus, that is the 0 state 7 in a particular subcycle. We want this reference vector, we are trying to produce only with these 2 active vectors and this 0 state alone. So, how do you do? You start from here, let us say you apply this 0 state 0 for the entire tz seconds, not half of tz, not 50%, 60% or 70% of tz. For the entire tz you apply minus minus minus. Then at the end of tz you switch your R phase and you go to plus minus minus and stay at this state for t1 seconds, and then you switch your Y phase and stay there for t2 seconds. That would be the end of your subcycle. Now, in the next subcycle what you do is you stay here and apply this vector for t2 seconds or t2 dash seconds. Then switch your Y phase and come here and apply the active state 1, stay here for t1 dash seconds. Then what do? You switch your R phase and go back here and apply this state for tz dash seconds. So, you can this is what I would call as clamping sequence 1. This is a different sequence, earlier sequence we call it as conventional sequence. You start from this 0 state, go to active state 1, active state 2 and go to the other 0 state. Now, you are skipping one 0 state and I am calling this clamping sequence. Why am I calling clamping sequence? Because you see here minus minus minus, all the 3 phases are connected to the negative bus. Here R phase gets connected to positive bus and here Y phase also gets connected to positive bus, but you look at B phase, it is negative here, it is negative here, it is also negative here. What does it mean? B phase is not switched at all, B phase is clamped to the negative DC bus over the entire subcycle. Therefore, we call the sequence as clamping sequence. This is clamping sequence. This is one possible clamping sequence. There is another kind of clamping sequence. What is that? You can totally ignore this 0 state minus minus minus. Instead, you can use the 0 state plus plus plus. So, let us say you start from plus plus plus. You apply this for tz seconds. Then what you do? switch your B phase, you go to plus plus minus, stay there for T2 seconds, then switch Y phase, go to active state 1 and stay here for T1 seconds. That is the end of subcycle. The next subcycle, stay here for T1 dash seconds, switch Y phase, go to active state 2 and stay here for T2 dash seconds and switch B phase and stay here for Tz dash seconds. So, this is again another clamping sequence. Now, what happens? Minus 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 is never used and only plus 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 is used, and therefore, you look at the 3 states. Now, here all of them are positive, here R and Y are positive, here R alone is positive, and you can see that R is positive everywhere, and therefore, R phase is getting clamped to the positive DC bus here. So, the earlier case it was B phase getting clamped to the negative bus, in this case it is the R phase getting clamped to the positive bus. So, this is I am calling as clamping sequence 2, just you have to give some name and you have to distinguish between this and that. So, the earlier clamping state uses the 0 state minus minus minus, this is the clamping sequence which uses the 0 state plus 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 and avoids the other one. So, I am showing the same thing versus time, the horizontal axis is time here. So, the states are applied 0, 1 and 2 are applied for durations T0, T1 and T2, and in the next subcycle it is applied for times T2 dash, T1 dash and T0 dash. As I told you before, at steady state the Vref will be same for both of these cases, but the alpha will be different, and therefore, your T2 dash and T1 dash will slightly differ, the dwell times will differ. That is why I am calling T2 dash instead of T2 and T1 dash instead of that. The difference is of course small, and sometimes you can also use the same dwell times in a pair of half carrier cycles. So, that is also fine, right. Okay. So, one would be called an asymmetric sampling, other one would be called a symmetric sampling. This is an asymmetric case. The other case, when you have the same T2 and T1 used here, you would call it a symmetric sampling. Alright. So, now let us see with the other clamping sequence, again you get the same kind of situation now. So, the difference, let us go back and see, R phase switches here like before, except instead of Tz by 2, this is equal to Tz. So, for Tz seconds it is low and then goes high like this now. How about Y phase? It switches here. The R phase duty ratio is lower than what it was with conventional sequence. The Y phase duty ratio is also lower than what it was with conventional sequence, and B phase duty ratio is also lower than what it was with the conventional sequence, and the B phase duty ratio is 0. The B phase duty ratio is 0. It is always connected to the negative bus, and its average value is equal to minus VDC by 2. So, you can't go lower than that. So, you are doing like this. This is now B phase is getting clamped to the negative DC bus. In the other case, you see that the R phase is getting clamped to the positive DC bus. What has happened here? The conventional switching sequence, the difference between here and there, the duty ratio of R phase is increased and it has become equal to 1. You can't go higher than that, it is 1. And then the duty ratio of Y phase is also increased and that of B phase is also increased now. This is R phase getting clamped to the positive DC bus now. So, now if I use only one 0 state throughout, this is only one 0 state in one half carrier cycle, this is the same 0 state in the next half carrier cycle also. So, you find that R phase is clamped here and you also find that R phase is clamped here now. If you kind of use the same kind of sequence everywhere, what will happen? R phase will continue to be clamped to the positive DC bus over that entire sector at least. So, now this is what I am trying to do. I am using 7 to 1 and 1 to 7 in alternate subcycles in sector 1. So, 7 meaning plus plus plus, 2 meaning plus plus minus and 1 meaning plus minus minus. So, what happens is R phase is getting clamped to the positive DC bus here. Let me just write it down. Let me write down, I am sorry. Oh, sorry. R phase is clamped to the positive DC bus here. Next, what happens? You just look at the previous case here 7 6 1, if it is 7 it is plus plus plus, and if it is 6 this is plus plus plus, 6 is also plus minus plus and 1 is also plus minus minus. So, in all the cases R phase is clamped to the positive bus. R phase is clamped to the positive bus over the entire sector. In every subcycle in sector 1 it is clamped to that, in sector 6 also it is clamped to the positive bus now. Let us go to the next sector 7 2 3, 7 meaning plus plus plus, 2 meaning plus plus minus and 3 is minus plus minus. Here you find that Y phase is clamped to the positive bus. See, this is Y phase is clamped to the positive bus in every subcycle in sector 2. And how about sector 3? 7 4 3, 7 is plus 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 and 4 is minus plus plus and 3 is minus plus minus. Here again you find y phase is clamped to the positive bus in every subcycle in this one. Therefore, just what is remaining, it is not very difficult to guess that in the other two sectors B phase is going to be clamped to the positive bus. Let us just check that 7 4 5, 7 all of them are positive, between 4 and 5 you look at. So, between 4 and 5 plus what is positive in both cases, it is B is positive and plus 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 also B is positive. So, B is clamped to the positive bus in this entire sector. Here again B is clamped to the positive bus in the whole sector. So, this is what you get. So, for entire 120 degree R phase is clamped to the positive bus, Y phase is getting clamped to the positive bus for another 120 degree, B phase is getting clamped to the positive bus for another 120 degree now. So, we can just also do the same thing using, there is just to emphasize the equivalence between this and the triangle comparison approaches. You can apply this 1 to 7 or 7 to 1 for example. If you are doing that, what you get, I showed you that VRO is always positive, VYO switches like this and VBO switches like this, VBO switches like this, and you can once again look at what is VRO average. VRO average is same as VRO itself and you can consider an equivalent MR star, and VYO, as this VYO average is shown by the dashed line here, and that the MY star is a scaled version of that equivalent modulating signal. Similarly, VBO average is now something very close to 0 in this case and it is MB star now. MR star, MY star and MB star can be compared with a triangular carrier as we did before. And if you can start with MR star, MY star and MB star, or you can start with MR, MY and MB and add a suitable common mode component, we do not know what it is exactly, but if you can find out, you can add that common mode component MR star, MY star and get MR star, MY star and MB star, and you can simply compare with triangular carrier. So, the switching instance can be determined either from the space vector point of view or from the triangle comparison point of view if you are using these sequences now. So, how would your equivalent modulating signals be? This is how the equivalent modulating signals will be if you work it out. And as I showed you, R phase is positive in two sectors for 120 degrees here, and this is Y phase is positive for the next two sectors and B phase is positive for the next two sectors. And what you are actually adding is a positive common mode component. As we were discussing earlier, there is a positive common mode component and there is a negative common mode component is possible now. So, here what are you doing? You are taking the phase which is going to the maximum value V max and you are subtracting Vp minus V max to get this common mode component, and R phase has got the highest value between this 30 to 150 degrees as the most positive. You are subtracting V peak minus R phase and that is your common mode component. The next 120 degree you are doing the same with the Y phase instead of R phase and the next 120 degree with the B phase instead of R phase, and so your common mode component is like this. This is what we did as 120 degree clamp. We saw one example here and this is what you is it now, and it is bad in one sense. Why? You see that the duty ratio here it is very high and it never goes that negative, that is the top device is continuously on here. So, the conduction loss in the top device is much higher than the conduction loss in the bottom device and that is going to lead to an uneven loading of the top and bottom devices. So, what we studied as 120 degree clamp here is same as what we saw here a while back. This is to show the sequences, this is show that they are equivalent at a subcycle level, and this is how the modulating signal is going to be. Here the MR star, MY star and MB star are there. This is only to indicate how MR star, MY star and MB star are, and this is the common mode component. If you subtract that common mode component from MR star, you will get your original MR, or you start from MR, MY, MB, you add this common mode component, you get this MR star, MY star, MB star, compare with triangular carrier, you can produce the same PWM signals, right. Next, let us say instead of the 0 state 7, I use only 0 state 0 throughout. You see that everywhere it is 0 is written and 7 is never written in the sequences now. In the entire sector 1, I use 0, 1, 2, 2 and 0. So, 0 meaning minus, minus, minus. I do not use the state plus, plus, plus at all. So, here what will happen? Let us just write it down. Which phase is going to be clamped? It is B phase which is going to be clamped, and B phase is going to be clamped to the negative bus. How about here? It is 0, 2, 3, 0 meaning minus, 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 2 meaning minus, plus, minus, and here it is plus, minus, minus. So, here again it is B phase is going to be clamped to the negative bus. Now, you look at the next sector, it is 0, 3, 4, 0 is minus, 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 3 is minus, plus, minus and 4 is minus, plus, plus. So, R phase is always negative and therefore, here R phase would get clamped to the negative bus. And if you look at the sector 4, The states used are 0, 5 and 4, and 0 meaning minus minus minus, and 5 is minus minus plus, and 4 is minus minus plus, and it is always minus here everywhere. This is B phase is always negative. Therefore, I am sorry, R phase is negative. So, R phase is negative here. How about the next one? You see that 0, 5, 6 and 6, 5, 0. 0 is minus minus minus, and 5 is minus plus minus, this is minus, and here in 6 also it is minus here. So, Y is negative everywhere here. So, in this if you use these sequences, in every subcycle in sector 5 you have Y phase clamped to the negative bus, and similarly in sector 6 also you will have Y phase clamped to the negative bus now. So, here instead of every phase getting clamped to the positive bus for 120 degree, you find a situation where every phase is getting clamped to the negative bus for 120 degree, very similar to the other 120 degree clamp method we saw before. Just you can to emphasize the equivalence, you produce 0, 1, 2 etc. This you can come up from the space vector point of view, that is start from the revolving vector and sample and calculate the dwell times and output the states. From there you get VRO, VYO and VBO as indicated here. The same 3 phase pole voltages can be produced by considering these MR star, MY star. Now, this is VRO average, VYO average and VBO average. MR star, MY star and MB star are scaled versions of that. You can start with MR, MY, MB, add some common mode component such that you get these MR star, MY star and MB star, and you can compare it with the triangular carrier now. So, the only question is what is this MR star, MY star, MB star, and what is the common mode component to be added? The answer is here. Your MR star is actually this, while this sine wave is the original MR, your MR star is this. Similarly, MY star, MB star, and what is the common mode component? This is the common mode component. This is the negative common mode component. This is again bad in one sense, because the bottom devices will have greater conduction losses than the top device would have, and the top and the bottom devices will have unequal loading, will have different levels of dissipation now. So, as we saw earlier, the common mode component, if you want to do bus clamping, you should either add the positive common mode component, so that one of the phases will get clamped to the positive bus, or the negative common mode component, so that the one of the phases the M min would get clamped to the negative DC bus. Now, what we saw was if you add this throughout, what happens? The average value itself shifts to the positive, or if you add the negative common mode throughout, then the negative gets shifted to negative value, and therefore, it is either the top and the bottom devices are going to be loaded unequally. So, this is what happens. Now, we are looking at the same thing from the space vector point of view. So, if we do not want this unequal loading, you want equal loading of all 6 devices during bus clamping. Now, when you are doing bus clamping, that is you are going to use only one 0 state in a subcycle, still you want equal loading. What you should do? If you use one 0 state, let us say 0 or minus 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 in a particular subcycle, then you should use the other 0 state 180 degrees later. So, this must be needed for half wave, only then the top and the bottom will have the same amount of losses. And the same way, if you are using a particular 0 state 0 in this subcycle, 120 degrees later you must use the same 0 state, only then whatever is condition subjected to R phase, the same condition Y phase will also be subjected to, and the B phase will also be subjected to that. Now, the first condition is a half wave symmetry condition, and the second condition is a 3 phase symmetry condition. So, you combine these two, what you will get is the 0 state employed must be changed once in every 60 degree R sector. It must be changed once in every 60 degree R sector. That is the rule. Now, earlier we can say that you should follow this for 60 degree and follow this for 60 etc., etc. Now, I am just trying to put that idea in terms of 0 state. The 0 state must be used once in every 60 degrees. And how are you going to do that? One example is the 60 degree clamp. We are going to change the 0 state in every 60 degree. Where am I changing? Now, let us say I use the 0 state 7, 721, 127 etc. is used in the alternate subcycles here. I am just writing 721. What do I mean by 721? If I use 721 in the subcycle, in the next subcycle I will use 127. So, 721 and 127 will be used in the alternate subcycles is the meaning here. So, I use 0 state 7. I change the 0 state from 7 to 0 at the middle of sector 1. This is at 30 degree line. Right. Then I start using 0, 1, 2, 0, 1, 2, 2 and 0. I move to sector 2, but I still continue to use the same 0 state 0. So, I use 0, 3, 2, 2, 3, 0 would be the switching sequences I will use now. At the middle of sector 2, I change from 0 to 7. So, again at the middle of sector 3, I change from 7 to 0. So, you can see that I go on like this, 0 state 7 is used here, 0 state 0 is used here, 7 is used for 60 degree, 0 is used for 60 degree. So, I am changing once in every sector. Where I am changing? I am changing at the middle. I am changing at the middle. I am changing from 7 to 0 in sector 1, I am changing at the middle. If I do this, what will happen? Let us just see. So, if you say 7 to 1, what happens is R phase is getting clamped to the positive bus, you are avoiding the 0 state 0, that is minus minus minus. So, R phase will get clamped to the positive bus, and here also what will happen, R phase will get clamped to the positive bus, and if you go around you can see that is 0 1 2. So, minus minus minus, 1 is plus minus minus, and here plus minus minus, you can see that B is clamped to the negative bus here. Again in this 30 degrees also B is clamped to negative bus here. You go a little further, now this is R phase is clamped here around active vector 1, around active vector 3 Y phase should be clamped, that is what is 3 phase symmetry, right. So, it will be Y plus and Y plus here. The same way you can see from half wave symmetry, if it is R plus and R plus here around vector 1, it will be R minus and R minus here. Okay. The same way you can say this is going to be B plus and B plus here, and what do you have here, Y minus and Y minus. So, you can see that every phase is now getting clamped to a bus for 60 degree duration now. R phase is getting clamped to the positive bus for 60 degree, followed by B phase to the negative bus for 60 degree, and then Y phase for the positive 60 degree and R phase to negative bus for 60 degree, and so you go around both these things now. What is this? This is the earlier 60 degree clamp we saw. So, this is nothing but you are following the positive common mode and the negative common mode alternately like in this fashion, and you see that R phase is clamped during the middle 60 degree duration, Y phase is clamped during the I mean every phase is getting clamped during the middle 60 degree duration of a positive half cycle. So, now this is R phase, it is the positive half cycle of R phase, this is the middle 60 degree duration of the R phase, it is getting clamped to the positive bus. Similarly, this is the negative half cycle of R phase, during the middle 60 degree duration it is getting clamped to the negative DC bus. Similarly, R, Y and B. So, what we did as 60 degree clamp here by adding common mode component is the same thing being done this way, right. Then now you look at the other way, again I am changing the 0 state at the middle of every sector, but the change is now from 0 to 7, that the other way now. So, if I do like this, you can see what the states are now. So, in this case what will happen in sector 1, R is getting clamped to positive bus here, and this is getting clamped to negative bus here. With some more study you can also find that R would get clamped to the positive bus here, and in this case it would be Y getting in 0 1 6, if 0 is minus minus minus, 1 is plus minus minus, and here it is plus minus minus, it would be Y getting clamped to the negative bus here. So, you can go about doing the same thing in the various situations, you will find that it is R will be minus here, and here again R would be minus here now. So, if you look at this, this line corresponds to 90 degrees, this line corresponds to 90 degrees, that is the R phase is going through the peak. So, that is the instant 90 degree now. So, this line is 60 degrees, that is at the instant 60 degree the vector will be aligned here, and this is 0 degree. At the instant 0 degree the vector will be aligned here, at the instant 30 degree the vector will be along this axis, and this is 60 degree, this is 90 degree and so on. So, what you find is R phase is clamped between 30 and 60 degree, and similarly R phase is clamped between 120 and 150 degree, this is 150 degree, is clamped between 120 and 150 degree. So, R phase is clamped during, if you take this, this is 1 quarter cycle, just 1 quarter cycle 0 to 90 degree, R phase is clamped during the middle 30 degree duration of every quarter cycle, again it is clamped during the middle 30 degree duration of this quarter cycle. Similarly, R phase is clamped during the middle 30 degree duration to the negative bus, here again R phase is clamped to the negative bus. So, the PWM signal would look like this, the MR star, MY star, the equivalent modulating signals would look like this. You see that the R phase is clamped like this to the positive bus, here it is clamped to the negative bus, and the modulating signal added is shown here, this dashed line, blue line, this line dashed blue line. Okay. So, this is 30 degree clamp, you can start from the 3 phase sine waves and add this common mode component and get these modulating signals and compare them with triangular carrier and do the generation, or you can do it the same way. So, either you do it from the space vector point of view or the triangle comparison point of view, you are going to generate the same PWM waveforms at the end, right. This is what you are going to get now. This 60 degree and 30 degree are special cases now. Continual clamp is a general case of our earlier 30° clamp, I mean 60° clamp. Earlier from 721 to 012 we changed at exactly at the middle, 721 to 012 we changed at the middle of the sector. Now, it does not have to be at the middle of the sector, it is at certain angle gamma. This gamma is equal to 30 degrees is a special case. The gamma can be anywhere between 0 and 60 degrees, it can take any value between 0 and 60 degree now. So, this would lead to R phase getting clamped. Where would R phase get clamped? You can see that R phase would be clamped over this interval, R phase will be clamped over this interval and R phase will get clamped to the positive bus. Similarly, R phase will get clamped to the negative DC bus over this particular interval now. Again, so R phase is continuously clamped for 60° duration, it is continuously clamped for 60° duration. Here again it is continuously clamped for 60° duration to the negative bus. Therefore, we call it continual clamp PWM and the modulating signal would look like this now. So, this depends on the value of gamma where exactly, and this it can start from here for 60° duration. This can be as low as 30 and as high as 90 degree, and this instant can be as low as 90 and as high as 150 degrees now. So, this is your R phase signal, this is the MR and this is the MR star, this is the modified R phase modulating signal. So, what you can do is again you can start from sine wave as shown here and then add a common mode component as shown in the dashed line which we discussed before and get these kind of modulating signals as shown in the solid red line and so on and compare with triangular carrier, or you can do it from the space vector approach. Start with a circulating revolving rotating revolving reference vector sample and find out the nearest active vectors, calculate their dwell times and output the states, and you can do that again. So, this way or that way is the same for you, you will get with the same PWM waveform. The same thing about split clamp PWM method. So, what we did here was we had 721 here and 012 first, and here instead we have 012 first and 721 next. Those are the only two possibilities, and the changeover can occur at any gamma. The gamma can be anywhere between 0 and 60 degrees. So, now what will happen? You have R phase. This R phase is clamped to the positive bus in this interval, and here again R phase is clamped to the positive bus. So, this interval, these two intervals are not equal. As a special case, they can be equal to 30 degree. This interval is equal to gamma, this interval is equal to 60 minus gamma. So, for some interval gamma and some interval 60 minus gamma, R phase is clamped to the positive bus and you will find the same thing symmetrically everywhere, and the equivalent modulating signals would look something like this. So, this is split clamp PWM and you can see how they are equivalent. It is easy to see the idea of continual clamp and split clamp from the space vector point of view, because you have to change the 0 state once in a sector and that is at an angle gamma. You can use 012 first and 721 next and so on and so forth. So, this is split clamp PWM, and this is why I am just trying to say that the two are equivalent. So, they are approaches, both the 0 states are used by continuous PWM methods and only one 0 state is used by discontinuous PWM method, and the null vector time division is what determines the equivalent common mode component. Now, we will be emphasizing these points again and again for a while, and in the space vector PWM what we want to say is one active state is applied twice in a subcycle. There are some advanced bus clamping PWM which we will discuss specifically in the next one. This is a more general version of space to show that space vector approach is more general than triangle comparison approach. So, this is what we will do here. Quickly some references here, these are some papers on, this is a book and these two references are papers on this area, and this is a kind of which I have shown earlier also. This is a tutorial paper on this, and this paper is on the triangle comparison and the space vector approach. Thank you very much for your interest, and I am hoping to see you again in the next lecture. Thank you very much.